Hi, I'm Chris Brown, and this is Module 2.8, Intermediate Axiomatic Design. This module is about axiomatic design of manufacturing processes considering coupling. The content is from a paper that I will be presenting at the International Conference on Axiomatic Design in Portugal in the beginning of mid-September, late September in 2014. The objective of this module is to advance axiomatic design theory to improve manufacturing process development within the context of new product development. So this is important because manufacturing process development facilitates wealth creation. The better we do at developing manufacturing processes, the better we'll be at manufacturing. And manufacturing creates wealth. Manufacturing is key to economic competitiveness. If we can't do good manufacturing process development, we won't be competitive. Traditionally, most of the manufacturing costs are already built in to the new product before the manufacturing process development begins. And this is unfortunate because it makes it difficult to manufacture things as cheaply as they could be otherwise. So manufacturing process development should be considered along with new product development. Now, the state of the art in this goes back to the 1980s when people started talking about concurrent or simultaneous engineering, and in that case they meant that we should be doing manufacturing process design at the same time as we're doing product design. And this has been used extensively this way. And so the main thing is to get manufacturing engineers with the design engineers so that they could work together and make intelligent choices for the product based on the manufacturing process. So what we're going to be doing here is trying to advance the formalization of that in the context of axiomatic design and looking at different ways that this might be accomplished. So we're considering different configurations of the design domains and of the decompositions, trying to maintain independence and still be able to make the modifications. So we're here in developing the theory of axiomatic design and extending the theory of axiomatic design. So we can get into situations where coupling is introduced with manufacturing, and we can also get into situations where the manufacturing needs are not being considered when we formulate all of the process variables. Another thing to consider is that tool design. We don't always have the tools we need to make the products that we want to make. So sometimes we have to develop new tools along with new products and new manufacturing processes. And so we're going to look at how that could be formalized as well. First, though, let's consider an example problem that shows how coupling can be introduced into the manufacturing process development in the new product development. So this is one of my favorite examples because I also do work on surface metrology, and this involves some interesting issues in surface metrology as well. So rotating lip seals. So these ride on shafts. So this green element here is the rotating lip seal. So this rides on a shaft, and what we're showing here is just half of it. It goes around the shaft. And the shaft is turning. Things like internal combustion engines convert chemical energy to mechanical energy in oil-rich environments, and the oil needs to be retained inside the engine, but the power needs to get out, and we typically get that out through a rotating shaft. Another place where these are used would be in hydraulic pumps. So the power, when we're getting the power into or out of an oil-rich or fluid environment, with a shaft, we need to maintain a seal around that shaft. The roughness of the shaft turns out to be very important for the life of the seal, and so considerable work has been done on figuring this out. So while most people are not aware of rotating lip seals, in fact they're in all of our cars and all of the hydraulic pumps, and so there's considerable reliance on these kinds of things. And should the rotating lip seal fail, it's on your drive shaft and it's difficult to change. So the critical surface here that we're going to be studying is the surface on the shaft. Now, initially, the Rubber Manufacturers Association has 3 roughness criteria to specify the roughness of the shaft: average roughness, peak to valley roughness, and the peak height. And your intuition on what these are probably serves you right. We have the arithmetic average is the RA, and is the most commonly used roughness parameter. So we have 3 double-sided tolerances, making this one of the most toleranced rough surfaces there is. Now the problem is that we can't adjust these RA, RZ, and RPM independently. And let's see a little bit why. So this is from a paper that I wrote about surfaces in 1990. And we're doing a cross-correlation matrix. We're looking at covariance here. Now this was done previously by Nowicki from Poland, who suggested this as a way of looking to see what parameters might have more information about the surface that we would be interested in. And so parameters that are highly correlated, for example RA and RZ, will have a high value here in the covariance matrix. So in this particular work, RA and RZ are highly correlated. In fact, we can write an equation which is good to about 82%. In other words, if the R value is 0.9, we can square it and find out sort of what percentage of the time RZ, the variation in RZ, can be explained by the variation in RA. Similarly, with RPM and RZ, those are also highly coupled, and we can also write a formula, and that's good about 80 to about 84%. So if we know it's possible to write these equations for the abrasive process that we were using, then it'll facilitate hitting this multi-parameter tolerance. Let me illustrate how this works there. So the peak to valley roughness is indicated here. Let's take another look at that. So this would be the RZ here. And then the peak height would be from the mean line to the top. So this is the RPM. And so if we, for example, remove the peaks, as we might on a honing operation of a surface that had a profile like this, then we would have this kind of surface. Now the mean line would have to be adjusted, but so is the peak height. So the RPM is very much smaller, and so is the RZ over here, the peak to valley. The ratio, though, is changed remarkably, and it goes from about 1/2 to about 1/4 in this case. And this kind of surface is called a plateau hone surface. And the profile is called full. And it's a good surface for oil lubricated bearings, because the oil can go into the valleys, and we have and come out to under pressure and help provide a hydrostatic interface. So there's coupling, though, and the coupling, because we can't change these independently, needs to be addressed systematically during the decomposition of the design solution. To assist in that, target values, tolerances, and the relation between the elements should be defined by equations when we can do that. The resulting interactions can be then entered into the design matrix and the process matrices, and so that we can see how best to manipulate those, and we'll be looking at examples of this in a later module. So the coupling needs to be addressed during the decomposition, and it requires revising DPs based on the coupling with the PVs. So So let's take a look at manufacturing process design within new product design. 1 decomposition and 4 domains. So we're adding the process domain here. So we'll zig over from the customer needs to the FR0, DP0, and then have a PV0, and this begins the manufacturing process design. So then we would zag back across the physical domain all the way back to the functional domain, then begin another zig looking at the top level FRs, DPs, and PVs. Then we would go down to the next domain, looking to see if any customer needs apply, at the next level, looking to see if any customer needs apply at this level. And we would continue like this until the design solution becomes obvious. And so we're co-developing the manufacturing process design, reacting to the physical. So what we would have done in the previous problem would have been recognizing that we cannot change RPM and RZ independently, nor can we change RA independently of these. And so, we would then go back across the zig and say, all right, we need to have a specification of the design parameters that will allow us to independently process these and produce them independently in the processing phase. But let me go back here. In this particular case, there's a considerable experimental work that was done to determine what the RA, RZ, and RPM values should be. And so then that would require going back to the experiment, actually going back to the way roughness is being defined in this case, to try to find new roughness parameters that would have this property of being independently adjustable in the process phase. And this is considerably more effort, of course. So what are some of the difficulties? Well, the principal difficulty is there's nowhere to introduce the manufacturing requirements. And so we previously discussed what manufacturing requirements are. Manufacturing should add appropriate value and minimize cost. Now, I've shown the minimize cost here as a selection criteria. After studying Thompson's paper, I think this is a better way to characterize the cost issue in manufacturing. All right. So manufacturing process development, we could separate it then from the new product development in this kind of way. So first we would do the new product development, going from the customer to the process to the physical domain. And we would stop with the DPs. Then we would zag into another decomposition. So this is 2 decomps. And here we would start with the manufacturing process development CNs, which would be generated largely out of the new product development DPs. So we would use the DPs for the product to generate the customer needs for the process. And then we would develop the FR0 and the DP0 just as if this were a separate design, which in fact we're essentially doing. And then we can zigzag down to the lower levels, getting more detail on the manufacturing process. And so here we've got 6 domains, 1, 2, 3, 4, 5, 6, and 2 decompositions. So essentially we could finish the new product development design decomposition before we begin on the manufacturing one. Now, the problem here, if we think of the example of the rotating lip seals, is that there's no opportunity really to iterate back to the definition of the DPs of the surface roughness, which was causing the problem in the example. So this does not provide that kind of flexibility. However, we still need to trace the value chain back through to the end-use customer new product development CNs. We need to maintain those through the manufacturing process development so we don't lose sight of what's creating value. So we need to address the value added criteria in manufacturing this way. The additional manufacturing process development CNs would be supplied by the manufacturer, one of the stakeholders, obviously, acting as a customer or a stakeholder, as Thompson called them in this situation. So this would introduce elements for controlling cost and controlling waste. So therefore we would address the manufacturing requirements this way. However, we still would have the same sort of coupling with the shaft and with the roughness, and not have an ability to modify that. So essentially what we have here is sequential new product and manufacturing product decompositions. And this gets back to the problem essentially that initiated simultaneous or concurrent engineering, that we finish the new product development and then throw the results over the wall to the manufacturing people. However, we do get a complete new product development for defining the needs of the manufacturing processes. And we could save iterations through the manufacturing process development when changes are only needed in the new product development. But the problem, as I said, is design costs during the new product development cannot be addressed in the manufacturing process development alone, and hence the example on the surface. Let's think about the problem of tool design, which follows from the manufacturing process design development. Now this would be important in the case where there are no existing tools for this kind of manufacturing process. So this occurs times when, for example, integrated circuits were being developed. New tooling, new processes had to be developed to diffuse elements into silicon, to produce the silicon wafers. And so there's considerable development that was done at that time for the tooling. So how does this look? So as we complete the manufacturing process development DPs, we realize we don't have the tools to make those. So now we need to go to facilitate tool development matrix, or decomposition. And then we can develop the customer needs based on what the design parameters are in the manufacturing process development. Excuse me. And so then from the FTD CNs, we could develop the FTD, the tool FR0, DP0, and then go down to the FR, the top level, and the second level, and so forth, until the solution is obvious, continuing to decompose. Let's take a look at the PV definition. Now we've said a lot about what the FR should look like. We've noted that the DP should begin with a noun because it's a physical kind of thing, or perhaps an adjective. The new product development PVs should start with verbs. The process indicates an action. It's a process. It's applying energy to a workpiece to add value. Now, that's in the strictest sense of, say, a mechanical part. But also for modifying, say, an organization, this might require considerable energy, and we hope that it adds value. So there's certainly the physical part can serve as a kind of metaphor that we could use in other kinds of design problems. All right. So, so these are the manufacturer value adding the NPDs for the DPs for the NPD. For example, turn a cylinder or form threads. So let's take a look at these examples. So here's two different things. We may want to make a cylinder, for example, if we're making car engines. And there's so many places where we need threads. So the DPs would be the cylinder to fulfill some function. It doesn't really matter what at this stage. Then the threads would also fulfill some function. So the PVs would be something like turn a cylinder and form the threads. So in a sense, this NPD PV is the process solution. So, so now we have the new product development design parameters, cylinder and threads. And so we could say, well, what are the manufacturing process development, FRs? So now they have to be stated like an FR. So manufacture a cylinder, create threads. And we need to state this in such a way that it is solution neutral. So the FR should allow us design space in which to choose different ways to do this. So if we start with the FRs, then manufacture a cylinder and create threads, we might select the DPs of a turning process and a forming process. So the MPD DPs indicate the nature of the process. And the DPs must also be selected in a solution-neutral environment so that we have a design space available for the process variables. And they might also include some manufacturing system requirements as opposed to the more specific process. So let's take a look at the MPD design domain some more. So we might go from the DPs, a turning process, to the PV, turn on a lathe. For the forming process, to form threads with a tap. So we might have a thread forming tap as opposed to, say, a cutting tap. So here's what these things look like. Here's a piece turning on a lathe, sort of a close-up, and there's an example of a lathe. And here is a forming tap, and here it is being used with a fastener. So the NPD PVs are now the process solution. So design domains can be configured to address manufacturing process development and facilitate tool development. But the new product development DPs might have to be adjusted to eliminate coupling at the PV-DP level. And the PVs indicate the application of resources, energy, for example, to add value, and they should start with verbs. Thank you for your attention.